Characteristics of a salt. First of all, let me remind you what a salt is. A salt is an ionic substance. Sodium chloride is a salt. And you guys know that because we call sodium chloride salt in terms of its common name. But ammonium carbonate is also a salt. Why? Because it's got a cation and an anion. Anything that's ionic is considered a salt. That's just the generic name we call it. Okay, it's not exclusive to sodium chloride. If it's got a cation and anion in chemistry lingo, it's a salt. When these things dissolve, they form the cation and the anion, depending on how many chemicals there are in the original formula. These ions, as you saw already, can react with water. And depending on how they react with water, if they form hydronium, the solution is going to be acidic. If they form hydroxide, the solution is going to be basic. That's what this chapter is about, or this section is about, is that you take these salts, you put it in water, you have to know the chemistry. Is the solution acidic or basic? And there are certain guidelines to help you figure out whether these salts are acidic or basic. So let's take a look at these real quick. The factors that determines the acid-base strength are polarity, strong bond strength, stability of conjugate, and solvation of ions. So once we have these ions, you got to recognize whether they are strong, what type of acids or bases they are, and their relative strength. And these are the factors that determines the relative strength of an acid. So remember that if this is our line of strong acid, let's say this is acid 1, this is acid 4, and we say that this is strong acid trend, then their conjugates are going to be opposite. Their conjugates, conjugate acid 1, conjugate acid 2, then the base strength is going to be at the bottom. Okay, so if you know that you've got a strong weak acid, then its conjugate is going to be a very weak base. They're going to be complement to each other. So that's important, because if I give you a list and you don't have obvious information to make the relative comparison, convert it over to its conjugate and see if you can't make the comparison that way. So let's take a look at these factors right here. Polarity. When a chemical is polar, it basically means that the charge distribution on the chemical is going to be skewed to one side. The greater the polarity, the greater the acid strength, because basically the electrons are going to be going away from the hydrogen that wants to come off. Remember, the weaker the hydrogen to X bond, X might be a chemical that's holding onto the hydrogen, the weaker that is, the stronger the acid, because acid by definition wants to give up that hydrogen. So increase in polarity makes that chemical a stronger acid. Okay, bond strength. The weaker the bond between H and X, whatever X might be, it could be SO4 or F. The weaker that bond, the stronger the acid, because now that hydrogen can easily be removed. The stronger that bond, the weaker the acid. The weaker the bond, the stronger the acid. The stronger the bond, the weaker the acid. Think about that for a moment, okay? Stability of the conjugates. When that particular chemical releases its hydrogen, now it becomes an anion. That anion sitting in water, and if it can be stabilized by the water and it's stabilized that way, then that reaction has a good favorable outcome, because the products of that reaction are somewhat more stable. And then, of course, the solvation ions, that is when the ions can be surrounded by water, then it's very related to these two. Then it favors the hydrogen coming off. So let's take a look at, these are the definitions, okay? Acid strength involves the breaking of HA and the formation of water in general. Factors that affect the ease with which the bonds are broken and bond forms will is an indicator of acid strength. Okay, it'll give you a stronger acid. So let's take a look at these guys. These are called binary acids. And why is it binary? Because there's only two chemicals. That's why it's binary. It's hydrogen and the halogen. Okay, so these are binary acids. And the question is, which among these is a stronger acid? Well, in order to make that comparison, you need to look at the HX bond where X represents the halogen. Is this bond stronger or is this bond stronger? And what ends up, the argument here is that you have to look at electronegativity, but you also have to look at orbital overlap. Okay, again, these guys are binary, somewhat acid, because there's only two different types of atoms. Yeah, sodium hydride is not really an acid, but we can consider it an acid because it has a potential of giving up that hydrogen. Even CH4, it's got a potential of giving up that hydrogen. Ammonia we know is a base, but it has a potential of giving up that hydrogen. And HF we know is an acid because it's got a hydrogen to donate. What we're trying to do in this particular series is figure out which among these chemicals is more willing to give up that hydrogen. So let's take a look at this first. And what we look at here is the bond strength. You can see that HF has the strongest bond strength. That means it holds onto its hydrogen the most, which makes it a weaker acid. On the other hand, HI has the weakest bond strength, which makes it the stronger acid. All these are strong acids in water. But among the strong, HI is the strongest just because it has the weakest bond strength. Okay. Here is the electronegativity of sodium, carbon, nitrogen, and fluorine. Fluorine is more electronegative, definitely by sodium. That means that it's going to be more polar than this guy, which makes this a stronger acid than this guy. In fact, these guys right here are non-acid. They don't want to give up their hydrogens readily. So there are two factors for binary. One is bond strength. The other one is electronegativity. Here is the result. Let's take a look at bond strength. Okay, the reason why bond strength is a factor here is because hydrogen is a small atom. Fluoride, iodine is a very big atom. So atomic orbital overlap is very weak, which makes that bond very weak. Hydrogen is a small atom. Fluorine is a fairly small atom. It's in the second period. That atomic orbital overlap for the bond is pretty good, which means that that bond is stronger. So when you're talking about halogenated acids, that's what these are. We're looking at atomic orbital overlap. The less overlap you have, the weaker that bond, the stronger the acid. All these are strong acids, okay, because they have poor atomic orbital overlap. But among the strong, HI is the strongest. It's got the weakest bond. HF, remember our seventh strong acid? It's not in that list. The reason why it's not in that list is because it's got a pretty strong bond with hydrogen because of the atomic orbital overlap. That bond strength is 569. So it can give up the hydrogen, but not readily. If we take a look at these right here, fluorine is going to remove the electrons from hydrogen to greater extent than the sodium, because sodium doesn't have a big electronegativity. It doesn't want to pull in the electrons. So this bond between H and F is weaker than this bond between A and H. That's why HF is a stronger acid. In fact, we can look at the electronegativity and say that acid strength goes in that direction, base strength goes in that direction. It's always opposite. If strong acids are in one direction, then bases are going to be in the opposite direction because of this concept called conjugate. So that's what we see right here. Going up and down, you're looking at atomic orbital overlap. This is the strongest acid towards the bottom, the weakest overlap. Going across, however, you're looking at electronegativity. Okay, these are your strongest acid. These are non-acid practically. Let's take a look at oxyions. Okay, oxyions are acids that have this motif: oxygen, a third element, and some hydrogen that is going to be donated. So let's take a look at these series. These are called the hypochlorite ion acid. So this would be hypochlorous acid, hypobromous acid, and hypoiodous acid. Notice the hydrogens are not attached to the iodine, bromine, or the chlorine. Therefore, that's not a factor. You're not looking at atomic orbital overlap for these. What you're looking at is electronegativity. Which is more electronegative, the chlorine or the iodide? You guys know the chlorine is more electronegative. Therefore, it's going to be more polar. Therefore, this chemical right here is a stronger acid. There's a lot of chemistry there. It's a lot of chemistry that you guys have learned from Chemistry 200. You're applying it here to understand these concepts. Okay? Here, that's basically the trend. And indeed, this is the stronger acid relative to its sisters. Okay, if you change the number of oxygen, say we keep the second element consistent, chlorine, chlorine, chlorine and all, but now we change the number of oxygen. Oxygen is one of the most electronegative elements. It's only second to fluorine. That means that you're really withdrawing electronegativity from that oxygen-hydrogen bond, making this a lot weaker because the electrons are all going towards those oxygen. This is your strongest acid. That's why in our 7 strong acid, we said HClO4 is in that list, and HClO3 is in that list. That's HClO3, and that's HClO4. But HBrO4 is not in that list. Why? Because bromine is less electronegative than chlorine. Okay. So that's what we see right here. We see that these are the Kas. Bigger Kas are stronger acids. Okay. And likewise here, this will have a bigger Ka. So those are the trends that you will see in terms of when you have a series of chemical, which ones are going to be the stronger, which ones are going to be weaker. And basically you're making these arguments. You're using the chemistry of the chemical, the structure of the chemical and the chemistry that occurs to make that prediction. Okay, so that's what these are. Again, these are the oxyacids here, which is a stronger acid, H2SO4 or H2SO4. Well, sulfur is more electronegative than selenium. No wonder sulfuric acid is in our top 7, whereas selenic acid, that's what this is, selenic acid, is not in our top 7 because selenium is not very electronegative. Okay, I want to get through this and then I'll stop here. So the variation on oxygen again, because oxygen's electronegative. Here you can see that, remember, you're looking at the oxygen-hydrogen bond to see whether that's weak or that's strong. You've got one oxygen here that's pulling away from those. Here you've got 2 hydrogens pulling away from those. The more oxygen you have, the more polar that chemical happens to be, the more acidic it happens to be. Sulfuric acid indeed is much more acidic. H2SO4 is much more acidic than sulfuric hydrogen sulfide. Okay, hydrogen sulfide. That's this guy right here. Why? Because this has 4 oxygens, this only has 3. So again, this just shows you the Ka values and the pKa values for these different chemicals. And again, there's a trend here. When you have oxyions, you're looking at electronegativity or the number of oxygens. In fact, this chemical is so strong, it's got a negative pH. We'll talk about negative pH in the next section next week. Finally, the last thing I want to mention is organic acids. Organic acids are going to have this group. It's called the carboxylic acid. And what makes this acid strong is the R group. If R draws electron density away from that OH, then it becomes a really strong acid. If R doesn't draw that much electron density from that OH, then it's only a weak acid. Okay, and so these are examples of chemicals with carboxylic functional group. That's acetic acid. That's vinegar. That's formic acid. That's the poison that fire ants spits out, and that's benzoic acid. So you don't have enough knowledge as to which ones are good electron withdrawing group, but here are the pKa's. This one is a smaller pKa. That makes this one more acidic than this one. This would be first, most acidic. This would be second. This would be third. Smaller pKa leads to stronger acids, okay? Because stronger pKa, remember, the Ka is 10 to the minus. So this one's about 10 to the minus 3.7. This one's about 10 to the minus 4.2. 10 to the minus 3.7 is a bigger number than 10 to the minus 4.2. That's why this will be the stronger acid. So that's all I really want to talk to you guys about. Here we just talk about superacids. Look what happens when I change that hydrogen to fluorine. Those are really electron withdrawing. This is what we call trifluoric acetic acid. That acid is so strong, it's not readily available because it's a superacid. That thing has a negative pK, negative pH. So that's all I want to talk to you guys about. Next time, we'll take this concept of strong acid, strong base, and apply it to salts. Okay, we'll talk about that next time. Remember that your midterm is on October 28th. I'll give you more information next week about preparing for the midterm. We've pretty much covered chapter 16 here. The next section that we are going to be covering is titration curves. That's on chapter 17. And we'll do that next week. And then the following week, in fact, a week from Wednesday, we're going to have your midterm. And I'll give you guys more information on that. But that's all I really have for today. For those of you in lab, we have a midterm for the lab. I'm going to start at 6:30 to give you a preview and explain what those questions that you will see. Try and log in at 6:30. And then after our brief introduction, you guys can take the midterm quiz. You guys will have 2 hours to complete it. You have to complete it by midnight tonight, however. Okay. Are there any questions on what we talked about? I know we've talked about a lot of information. It's all in the realm of equilibrium. And you really got to know your chemistry if you want to understand what's going on in order to understand hydronium ion concentration, hydroxide ion concentration, pH of the solution. You might think of salts as a chemical you can put into water and it'll change the flavor. Salts are actually a generic term for ionic substance. When you have a cation and anion, what happens is that it breaks into its, when you put it together, it forms an ionic bond. And when you put it in water, it breaks up into its ions. That generally is classified as salts. Sodium chloride is a classic salt that you guys are used to, but you can also have salts of, say, iron chloride or sodium nitrate because you got a cation and anion. So certain salts, when you put it in water, it breaks up into ions, and those ions will react with water. And when they react with water, they can form either hydronium or hydroxide. The salts can either influence the pH of the solution to be acidic or basic. Some salts do neither, and you need to identify which salts will give you a neutral solution and which salts will give you an acidic or basic solution. Okay, so that's what we are covering today. We've already talked about, in this particular case, we finished up last time in terms of strength of acid. So given certain acids, you should be able to look at the property and determine which one are stronger acids and which one are weaker base, or weaker acids. But today I want to talk about salts. And the reason why I show this is because This is a list that I've shown a lot in the lecture class that we have. And up here, you will see that these are strong acids. Okay. Down here, you'll see that these are strong base. And in between, depending on these scales, you have weak acids that are strong and weak acids that are weak. And you also have weak base that are strong and weak base that are weak. It depends on the Ka and the Kb. That's what determines if you want to make a measurement. If you have the Ka and Kb, that is hands down the indicator as to whether something is stronger or weaker than another chemical. Of course, lacking a Ka or a Kb, you can just look at the structure and determine that based on our discussion last time. Okay, so that's what you need to know in this particular discussion. But let me just kind of give you the background of salts. When you have a salt, okay, you have a cation and an anion. And that cation could be some sort of metal or ammonium. Those are the common cations. The anion, of course, could be elemental anion, something like sulfur -2, or a polyatomic anion, an oxy anion like NO2 minus. That's a nitride ion. Now, remember that the salts could be something like MgS. That would be a salt. You know, that's the formula for magnesium sulfide, because magnesium's +2, sulfur's -2. So that's an ionic salt. You can put that in water, and if it dissolves, then it's going to give you the magnesium ion and the sulfide ion. Something like this, you have ammonium, let's say nitrite. You guys should know how to write the formula of these salts based on the charge of these ions. So ammonium nitrite would be a salt. When you put it in water, it will break up to ammonium and nitrite. What you need to recognize is, look at these ions and determine whether they are the conjugates of acids or base, because that's the key. If they're the conjugates of acids and base, then they can react with chemistry. I mean, they can react with water in order to give you hydroxide or hydronium. That's what you need to look at. So let me just give you an example of nitrite. Nitrite is the conjugate of nitrous acid. Nitrous acid is a weak acid. That means that NO2 minus is a weak base. In the presence of water, NO2 minus will react with water and form back its conjugate pair, nitrous acid. But where does it get the hydrogen? It gets the hydrogen from water, and so you form hydroxide. So if you have nitrous ion in solution, it's going to cause that water to give up hydroxide, and it'll cause that solution to be basic just based on that chemistry. So that's the chemistry of salts. So let me go ahead and go back here, because that's why I give you this list, because you got to know the conjugates so you know that they can react with water further, okay? So here are the examples. Strong acid, strong base. You know that for a strong acid, something like HCl, you should just know this, that when in the presence of water, hydrogen will donate its water and form hydronium ion and the chloride ion. The problem with hydrochloric acid, or I won't say it's a problem, it's actually the character of hydrochloric acid, is that the back reaction does not occur. Why? Because by definition, a strong acid is a chemical that donates its hydrogen 100% of the time. That means this guy can't pick up its hydrogen again from water, because in order to do that, it would form HCl, and by definition, HCl wants to dissociate. It doesn't want to stay together. So strong acids, they're always a one-way direction. They always break up through their ions. That means that their ions that they form do not go back and react with water and give you make the solution, a solution basic or acidic. It's this chemistry right here that influences the amount of hydronium that occurs. Likewise with base. You've got a strong base. By definition, it's going to dissociate 100%. It's going to form hydroxide and sodium. The hydroxide is not going to back react with water and get you back. It's not going to donate its hydrogen to water anymore and get you hydronium. It's not even going to rip off a hydrogen from water, because if it does rip off a hydrogen from water, you get a hydroxide anyway. So there's no chemistry involved. Strong acids and strong base, it's always a one-way street. However, a weak acid and a weak base will give you pH influence. That's why you see this right here. Okay, strong acid, strong base, 100%, but weak acid, weak base, they're not 100%. So if you have a salt from a strong base and a strong acid, an example of that would be, take that, and we'll take this, and you put that in water. It's got no pH influence because neither of the cation or the anion will react with water further. So it's going to be a neutral solution. Okay. On the other hand, salts from a strong base is not going to influence the pH. A weak acid, however, is going to it's going to be able to do some sort of reaction with water, and it's going to influence the pH of the solution. Likewise, weak base, strong acid is not going to influence the pH of water, but the weak base will, because it is the conjugate of a weak acid. And then when you have a weak acid and weak base, it will most definitely change the pH of the water. If you're asked to calculate the pH of the water, then you need to do some math. In fact, you need to do math for all of these. For this, you don't need to do any math. It's going to be a neutral solution. So let's take a look at that, okay? In terms of this, again, these are examples of the salts. This one will be acidic, this one will be basic, and this one you don't know, you have to do the calculation. So here are examples. I already talked about that. A basic solution. Why is this basic? Let me give you some background information. This is a strong base, so the barium is not going to do anything. Like barium hydroxide, the conjugate would be barium and the hydroxide. It's not going to do any chemistry, but the acetate comes from a weak acid. So if you have acetate, and acetate is this chemical right here, it comes from acetic acid. Okay, if you put a hydrogen on that, then it becomes acetic acid. So you can see that the acetate ion is the conjugate of a weak acid. Anyway, in the presence of water, the hydrogen will go back to that oxygen. You get acetic acid and hydroxide. That's why this solution is going to be a basic solution, because that conjugate in this salt will react with water and form hydroxide ion. That's where the chemistry lies. If we take a look at this next one right here, the strong base, weak base and strong acid, this is not going to influence the pH of the solution. However, a weak base, let's say we have ammonia, that's a weak base, but the conjugate of that is ammonium. Remember, ammonia is this guy, ammonium is this guy. Well, ammonium will react with water in this way. It's going to donate a hydrogen to water, and you're going to get ammonia back. But more importantly, you get hydronium as it donates that hydrogen. So this particular anion from this salt right here, from this salt, okay, is going to be, let's say we have ammonium chloride. This salt will give you a acidic solution, That's why the pH will be below 7. And any pH that's below 7, assuming we have 25 degrees, is acidic. pH above 7, assuming that we have a temperature of 25 degrees. Why 25? Because you got to remember, the neutrality is pH 7 when Kw is 1 times 10 to the minus 14. So this will be an acidic solution. You have to understand the chemistry in order for you to predict whether the solution is acidic or basic, and it comes from the ions that are in water. That's the key. And then for this, you can see that this chemical right here, ammonium acetate, will give you chemistry that looks like this, and the acetate will give you chemistry that looks like that. What you need to do is figure out which is the dominant reaction based on the Ka or Kb, and that's how you tell whether the solution is acidic or basic. On the other hand, if the question is to calculate the pH of the solution, you actually have to calculate the hydronium ion that forms or the hydroxide ions that forms. Calculate that, figure out which one is excess, subtract the limiting reagent, whichever remains will give you the chemical that is going to be what's left, and then you can calculate the pH from that. So that's the background in salts. You got to look at the ions that forms when you put it in water. Remember that in at least in general chemistry too, the solvent that we are using is always water, aqueous medium. So here are more examples. These are examples of the salts, but what I want to bring to your attention, of course, are these. Whenever you see strong base and strong acid, these are not going to influence the pH. If they're not going to influence the pH, then the pH is going to be 7, assuming 25 degrees. It's going to be a neutral solution. Here, only the anion is the conjugate of a strong acid, okay, like chloride, bromides, nitrate. So the cation will be responsible for the acidic properties of this salt. Here, what you have is, we haven't talked about this yet, but these are Lewis acids, salts. And you notice that these things have transition metals. Aluminum, it's got aluminum, chromium, and iron. In the next section, we'll talk about Lewis acids and base. And Lewis acids are those chemicals that want to accept electrons. And so transition metals are really good in accepting electrons. That makes them very good acid. And that's why these pH are below 7. Okay. Here, you can see that we have a strong base. And so the strong base is not going to influence the pH of the solution. It's the anionic portion that will influence the pH. And this, of course, right here, you have strong base as well. And this has a conjugate of a weak acid. When you have the conjugate of a weak acid, then it'll form its conjugate, of course. Weak acid will accept hydrogen and they will make the solution basic. That's why you see these right here, okay? So use this as a guide as to whether the salt will be acidic, basic, or you have to do the calculation. Here's an example of ammonium fluoride. Ammonium fluoride is one of those chemicals where you don't know whether it's acidic or basic. You have to do more research. And how do you do more research? Well, you know that ammonium is the conjugate of ammonia. So this solution right here in the presence of water will give you hydronium and ammonia. Okay, you just have to sort of remember that this is the conjugate acid of a base. So in water, this chemical will donate hydrogen because it's an acid. You get the original base back, but more importantly, you form hydronium. So this portion right here will make the solution acidic. The fluoride, however, is the conjugate of HF, which is a weak acid. So fluoride in water will remove the hydrogen from water. You get HF back, and you get hydroxide. So the fluoride in this particular salt will make the solution basic. So the question is, which one is stronger? Is the Kb, sorry, this is a Ka, okay, because you're forming hydronium. This is a Kb because you're forming hydroxide. You can always figure out what equilibrium constant to use because you look at the product and see whether hydronium is forming or hydroxide is forming. So what we need to do is we need to look at the Ka and the Kb for these species. And you can see that the Ka for ammonium is 5.56 times 10 to the minus 10. The Kb for fluoride is 1.47 times 10 to the minus 11. I can tell you right now that 5.56 times 10 to the minus 10 is bigger than 1.47 times 10 to the minus 11. This solution will be acidic. Okay, this solution will be acidic. So we can calculate the amount of hydronium that forms, okay, the amount of hydronium that forms and the amount of hydroxide that forms if we can do our little shortcut trick. 3.7 times 10 to the minus, or 37 grams of ammonium fluoride is 1 molar. Yeah, 1 mole, okay? The molar mass of ammonium fluoride is 19 comes from fluorine, 14 comes from nitrogen plus 4, that's 37. So if you have 1 mole in 0.5 liter, that's a 2 molar solution. That's a 2 molar solution. Why do we need molar? Because we need to know what the initial concentration of ammonium is and the initial concentration of fluoride. Now that we know that, we can calculate the hydronium ion concentration is equal to the square root of the Ka, YKa, we're forming hydronium. So that's 5.56 times 10 to the minus 10 times 2. And that's my hydronium ion concentration. You notice I'm just going straight to the shortcut. I don't need this ice table because look at those equilibrium constant. They're very, very small. Look at the initial concentration, 2 molars. That's pretty high. So I can just go to simplifying assumption. Here I can do the hydroxide ion concentration. That's equal to the square root of the Kb, which is 1.47 times 10 to the minus 11 times 2 molar. Okay. And you'll find out that the hydronium ion is a bigger number just because 5.56 times 10 minus 10 times 2 is going to be bigger than 1.47 times 10 minus 11. Let me erase this so that I can show you the results. And indeed, the hydronium ion is 3.3 times 10 to the minus 5. The hydroxide ion is 5.42 times 10 to the minus 6. Whenever you have hydronium and hydroxide, they're going to react with each other to form water. Whatever is left over is going to influence the pH of the solution. So I'm going to take the bigger number, 3.3 times 10 minus 10, subtract 5.42 times 10 minus 6. That's how much water is formed. And what remains is 2.79 times 10 to the minus 5 hydronium. I can calculate the pH from that. Okay. So this part right here, figuring out, this part right here, figuring out what chemical is in excess, that's just general chemistry. Okay, hydronium hydroxide forms water in a stoichiometric ratio. The limiting reagent will get used up and they'll subtract that amount from the excess. You calculate the amount remaining of the excess, and that'll be, in this particular case, the hydronium. Okay, so this salt, when you put the salt in water, it'll actually give you an acidic solution. Okay, it'll actually give you an acidic solution in the tune of 4.55 pH. So those are the type of problems that you will see in terms of here's a salt, acidic, basic, what's the pH? And you can calculate it. If you can do a problem like this, you can do a problem for any type of salts. You just have to recognize the chemistry. That's the key. If you don't recognize the chemistry, then you don't know what's going to happen when you put it in water. Okay. Let me go ahead and here are more problems of that. I'm just going to bypass this because these are more calculations of the same thing. We have um, this salt, ammonium bicarbonate. This is a lot more complex problem. You know the chemistry of that. It's going to form hydronium. The chemistry of this, however, is tricky because it goes back to baking soda. Remember when we had the baking soda problem, sodium bicarbonate? Then the bicarbonate can form carbonate ions and hydronium ions, but bicarbonate can also remove a hydrogen from water and form carbonic acid. And we did this problem last time, and we found out that the Kb of carbonic or bicarbonate is bigger than the Ka, and so that solution is so basic. It's the reason why baking soda is basic, because this guy follows this equilibrium. Anyway, what I do here is I calculate the hydronium ion concentration, the hydronium ion concentration from bicarbonate forming carbonate ion, and then I calculate the hydroxide ion calculation from bicarbonate forming hydronium and carbonic acid. Do the shortcut, okay? The square root of the Ka times, or in this particular case, the Kb times the initial concentration, that'll save you a lot of time. It looks like a difficult problem, but when you realize that these Kas are small, then it's okay to do the shortcut because you can do simplifying assumptions. You need to practice on these a lot so you are comfortable going directly from the chemistry to the shortcut reaction. Of course, the main, you are lost and you don't know whether or not to use these equations, the ice table will always be the fundamentals you go back to in order to figure out what the concentrations are. The ice table is the basic fundamentals that you are using. The shortcut is just the result from the ice table. Okay. So anyway, this particular solution is actually basic, and you can follow along in that calculation shown here. There's something called the leveling effect. The leveling effect is the reason why when you have HCl, HI, HNO3, okay, that all these acids are considered strong, even though in the last Wednesday discussion, I told you that HI was a strong acid than HCl. Why? Because there's less atomic orbital overlap. That means the hydrogen-iodine bond is weaker. That means the hydrogen is more readily to come off compared to HCl. But they're all considered strong because in water, all of these guys will form hydronium ion. And so you don't have HCl anymore. You don't have HI anymore. All you have is hydronium ion and their anion, I minus or Cl minus. That means that the strongest acid when you put HCl or HI in water is H3O plus. HCl doesn't exist. HI doesn't exist. It's H3O plus. And because H3O plus is common to all of these things, it's all going to be the same strength. Okay, it's all going to be the same strength. They're all equal in water. If you want to figure out that this is a stronger acid than this, then you need a different solvent. But you don't have to worry about that because in our class, we're using water as a solvent. Anyway, this statement right here, and it's also in your book, is that it's simply saying that among the strong acids, and there are 7, everything breaks down to hydronium. And since they all form the same conjugate, because they don't have a back reaction, then they're all equal in the eyes of water solution. That's called the leveling effects. You can't determine just based on chemical that you have, HCl or HI, one's not stronger or the other in water. Now, if you use ammonia as a solvent or acetate as a solvent, then the chemistry change because you're not looking at water to give up the hydrogen or accept the hydrogen anymore. You're looking at a different chemical, ammonia. Yes, you can have ammonia as a solvent. In organic chemistry, you guys are not going to be using water. You're going to be using organic chemicals. And organic chemicals can give you hydrogen or accept hydrogen. Okay. But that's for next semester. Anyway, that's the idea of the leveling effect. Okay. It's mentioned in your book. Now, the last thing I want to talk to you guys about in this particular section, this is the last section, chapter 16, is Lewis acids and base. We're going to learn about, or we're going to revisit this concept again when we go to chapter 22, coordination chemistry. But Lewis acids and base are defined in terms of the electrons being donated or the electrons being accepted. Remember, a proton is a hydrogen stripped of its electron, but the proton will seek out lone pairs to stabilize itself. So in terms of view, not in terms of the hydrogen or the proton, but in terms of the lone pair in which the chemical has to latch itself onto, we can define a acid as a chemical that has an electron site for donation, or we can think of a a Lewis acid as a chemical that will accept electron pairs, that will accept lone pairs. Just like hydrogen, sort of, instead of thinking of hydrogen latching onto water's lone pair, think of the lone pair on water latching onto the hydrogen. So hydrogen is a good electron acceptor, therefore it's a Lewis acid. On the other hand, a base will be a good electron donor, like ammonia. It has a pair of electrons to donate. That, because it's donating that pair of electrons, we consider it a Lewis base. So that's our definition right here. Lewis base, species with lone pair electrons to donate. Lewis acid, species with empty valence orbital to accept that lone pair. So this is the chemistry that occurs. And the reason why we use Lewis acids and bases because it's a more broad definition. Okay, it's a more broad definition. Yeah, if your computer died, don't worry. It's recorded and you guys can just look at the parts that you miss. So for this particular case, it's a more broad definition, and it's not exclusive to those chemicals with hydrogen or in terms of the Lowry-Bronsted. So this particular case is an acid-base chemistry, and you notice there's no hydrogen that is donated or accepted. It's simply lone pair electrons that are either being donated or being accepted. So this is a acid-base chemistry reaction in the Lewis sense, okay? Here is an extended definition of acid-base. So let's take a look at this real quick because let me see. There is no voice on this. Okay. Yeah, I'll do this. Let me go back to the original slide so that you can see what they are talking about here. Let me just get to that point and I'll share with you that movie. Okay. Switch screen. I'm gonna go right here. And I think you guys are seeing that. Okay, let's go ahead and play this.
Ammonia is a base in the Bronsted sense because it acts as a proton acceptor. For example, it accepts a proton from a water molecule to form the ammonium ion and hydroxide ion. In the Lewis acid-base theory, the emphasis is on the electron pair. Ammonia is a base because it acts as an electron pair donor toward the proton. The proton is an acid because it acts as an electron pair acceptor. Lewis acid-base theory is more general than Bronsted theory because it applies to systems that do not involve protons. For example, Ammonia acts as an electron pair donor toward boron trifluoride, a molecule that has a vacant 2p orbital. Ammonia also acts as a Lewis base toward metal ions, as in this example of the cobalt-3 hexamine complex. The ammonia electron pairs are donated into vacant metal orbitals. Carbon dioxide acts as a Lewis acid toward water. One of the unshared electron pairs on oxygen is donated to the carbon atom, as one of the CO double bond electron pairs is moved onto the oxygen of carbon dioxide. A proton from the water molecule moves to the oxygen of the carbon dioxide molecule, completing the formation of carbonic acid.
So that's the movie for Lewis acids and base. Let me go back to my screen here and wrap this up. So how does these type of reaction influence the pH of the solution? Remember, the pH is governed by the amount of hydronium or hydroxide is in solution. It doesn't look like there's any type of hydronium or hydroxide that occurs in this reaction. There actually is. Let me give you this example right here. Okay, these chemicals, iron, hexa, aqua, these are transition metals surrounded by water. What happens is that the metal has such a strong affinity for the electron density that the water that binds it, okay, the electron density is being shoved over towards the metal, that these things starts to weaken, and once they start to weaken, then they can come off. Okay, and that's the chemistry that occurs with these metal ions. If you take a look at the iron, you can see that you get one of the water forming hydroxide and you get hydronium. The fact that you form hydroxide doesn't make that solution basic. It makes that solution acidic because you're forming hydrogen ion as that hydrogen splits from the water. It leaves the OH bound to the metal, but the hydrogen ion is now free in solution, therefore increasing the hydronium ion concentration, making the solution acidic. So that's what occurs. In fact, what you can see in this table right here is the Ka's for these transition metal ions in water. If you put these transition metal ions in water, it's not going to be neutral. It's going to surround itself with the water as it binds to the water, and one of the water is going to lose its hydrogen because of the chemistry that occurs. And that's what you see right here. This is the example of the chemistry that occurs. Aluminum +3, you put that in water, it surrounds itself with water, it's going to be hydrated. But what happens is that it's such a strong pull towards that metal that it weakens this bond right here, and then that hydrogen pops over to water and you form hydronium. That's exactly the chemistry that occurs, and you have that solution as acidic, and that's why you have Ka values for these. They're still small, 10 to the minus 3 all the way to 10 to the minus 10, but they're comparable to some of the weak acids that we've seen in the past, and they certainly influence the pH. So we are going to revisit this again when we do coordination chemistry, chapter 22, but know that the definition is extended beyond the Lowry-Bronsted. Now we have the Lewis definition, okay? We have the Lewis definition. So this is a summary, and we're pretty much done with chapter